Welcome friends, Igor is here, and in this video we will learn how to transpose matrices. In this lesson we will define the operation of transpose of a matrix, we will define the notion of a symmetric matrix, and we will discover several interesting properties of the transposes. Let's get started. Given an m by n matrix A, its transpose is the n by m matrix, and this new matrix is defined as follows. The entry in position ij of the transposed matrix is the entry in position ji of the original matrix. Here is an illustration how to transpose a matrix. We start with a 3 by 4 matrix D, and its transpose is going to have size 4 by 3. There is a quick visual way to construct the transpose of a matrix. Essentially, when you transpose the matrix, the rows of the original matrix become the columns of the transposed matrix. So we take the first row of the original matrix D and we write it as a first column in the transposed matrix. Then we take the second row of the matrix D and we write it as a second column of the transposed matrix. And finally, we take the third row of the matrix and we write it as a third column of the transposed matrix. Now that we defined the notion of a transpose of a matrix, we can define the notion of a symmetric matrix. A matrix is symmetric if its transpose is equal to the matrix itself. Here is an example of a symmetric matrix, and you might not immediately see why this matrix is symmetric, so here's a visual cue. Look at the main diagonal of this matrix. The symmetry property is as follows. If you reflect this matrix about the main diagonal, the matrix does not change. And in case of square matrices, taking the transpose is exactly the operation of reflecting the matrix about its main diagonal. Notice that in this symmetric matrix, the first row is the same as the first column, the second row is the same as the second column, and so on. So when you switch rows and columns, the matrix remains the same. Let's make an immediate trivial observation that a symmetric matrix must be a square matrix. This is because when you take the transpose of the matrix, the m by n matrix becomes an n by m matrix. And for the two matrices to be equal, they have to have the same size. Therefore, the number of rows must equal to the number of columns. Now, let's see how the transpose works with the operation of matrix addition. And the result is fairly simple. Transpose distributes over matrix addition. To prove that two matrices are equal, first we have to check that they have the same size. If both A and B have the size m plus n, then A plus B has the size m plus n, then taking the transpose makes this into a matrix of size n by m. On the other hand, A transpose has size n by m, and B transpose have size n by m. When you add up two such matrices, the result is a matrix of size n by m. Therefore, the matrix on the left-hand side and the matrix on the right-hand side have the same size. The size is n by m. Now that we checked that two matrices have the same size, we will check that they have identical entries at every position. For this, we are going to look at the entry in a generic position ij of the matrix on the left-hand side. First, we are going to use the definition of the operation transpose. The entry in position ij of the transpose of the matrix is the same as the entry of the original matrix, but in position ji. We switch the indices for rows and columns. Next, we are going to use the definition of matrix addition. The entry in position ji of the matrix A plus B is the entry in position ji of the matrix A plus the entry in position ji of the matrix B. Now, we use the definition of transpose again. The entry in position ji of the matrix A is equal to the entry in position ij of A transpose, and the entry in position ji of the matrix B is equal to the entry in position ij of the matrix B transpose. The last step is to use the definition of the addition of matrices. But now we have proved that two matrices have identical entries and therefore they are equal as matrices. Next, let's prove that scalar multiple commutes with the operation of transpose. Namely, you can first scale a matrix and then take the transpose. This is the left-hand side of the equation. Or you can first take the transpose of the matrix and then scale the transposed matrix. This is the right-hand side of the equation. The result is going to be the same. Again, we start by checking that two matrices have the same size, and then we proceed to look at the entries. The entry in position ij of the transpose of the matrix alpha A is the entry in position ji of the matrix alpha A. But this entry is equal to the entry in position ji of the matrix A multiplied by the scalar alpha. The entry in position ji of the matrix A is equal to the entry in position ij of the matrix A transpose. Finally, we use the definition of scalar multiplication. This verifies that the two matrices have identical entries and therefore they are equal as matrices. Finally, let's prove that transpose of the transpose gets you back to the original matrix. First, let's check the size. If the matrix A has size m by n, then taking transpose once makes it into a matrix of size n by m, and taking transpose one more time switches the dimensions back into the original positions. It's an m by n matrix. Now we are going to look at the entries of the two matrices. So the entry in position ij of the transpose of A transpose is the entry in position ji of A transpose. So essentially we translate the outer transpose in this case. But now the entry in position ji of A transpose is the entry in position ij of the matrix A. This shows that the two matrices have identical entries, and this completes our proof that they are equal as matrices. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will learn how to multiply matrices. I will see you later.